Hello, my name is Dalton, and I'm an engineer at CTR Electronics. Today, we're going to be taking a closer look at the CTR Electronics CANrange, a powerful and versatile sensor designed to integrate seamlessly with FRC team robots over the CAN bus. Today, we're going to be taking a closer look at the electrical and mechanical specs and why teams love it. The CANrange is a time-of-flight sensor provided in a molded and robust package. It is compact and lightweight, weighing under an ounce with a footprint of less than 1.5 inches. On the CANrange are two 440 compatible 1-inch space mounting holes for mounting on a variety of mechanisms. Wiring is as simple as connecting power and CAN to the connectors on the bottom of the CANrange. I previously mentioned that the CANrange is a time-of-flight sensor. Let's talk about what that really means. The CANrange can accurately measure distance by sending out a low-powered infrared laser across space such that it hits an object and bounces back into the CANrange. By measuring the time it takes for that light to return back to the CANrange, we can accurately measure distance. One thing we should cover is the LED states of the CANrange. I went ahead and disconnected one of the candles to help highlight that a little bit better. So you can actually see that there's this ambiently orange light blinking really rapidly. In this rapid blinking state, you can actually see distance and whether or not we're detected or not. So first thing I want to show is how do you know, just looking at the CANrange, if it thinks it's detected. So if I put my hand in front of it, it transitions into a rapid green. Rapid orange, we're not detected. Rapid green, we're detected. The other thing that the LEDs indicate when CAN is functional and when the device health is good is that the speed of the blinking actually corresponds to detected distance. So it's hard to tell in this threshold because the total distance between my hand and the aluminum box tubing is a little short, but the faster blinking indicates how that the measured distance is closer, and you'll see slower blinking when the measured distance is farther away. And you can get a kind of rough idea of what that would look like in terms of meters by just plotting tuner and seeing how those values change. Let's talk about how far the CANrange can actually measure. We actually provide a couple of different configuration options depending on what you want to optimize for. The first of which is long range mode. In long range mode, you have 3 meters of detectable distance at up to 50 Hz update rate. However, you're a bit more sensitive to ambient light. The other option is short range mode. In short range mode, you actually have updates up to 100 Hz. You're more resilient to ambient light, but you're limited to 1 meters of update rate. If you know your measurements are going to be within 1 meter, you should be using short range mode. If you know your measurements are going to be within 3 meters, you can use long range mode. A common question that gets asked is how can we know if our distance measurements are accurate? Sometimes you are in an environment where there's a lot of ambient light, or the object you are detecting against is semi-translucent, and we'll talk a little bit more about that later. You can actually use the signal strength signal provided by our API to see how ambient lighting, different environments, and different materials will affect your distance results. Let's take a look at this simple demo I have here. I have a CANrange that is connected over CAN to a canivore connected to a Linux ARM64 machine with 2 candles. These candles, the right one indicates detected state and the left one indicates distance. So as I put my hand in front of the CANrange, you can see that this candle transitions into green, which indicates that I'm within my threshold for determining detected. And then as I move my hand away, you can actually see this candle transition. So now we're not detected. And then as I get closer, you can see that our distance is getting way closer and we maintain that detected state. So we're going to take a look at how this demo works. So I already have tuner pulled up and connected to my machine here. So I'm going to go ahead and click on this CANrange here. And let's go ahead and get a couple of signals set up. We care about the distance signal, the signal strength signal, and we care about the is detected signal. So let's go ahead and take a capture here. So let's go ahead and hide signal strength and is detected. Or let's go ahead and actually hide the other two and just only show distance. So we can see here that our ambient distance, so the distance between the CANrange to the box tube right here is give or take 0.16, 0.17 meters. You can see it's a little bit noisy and you'll need to make sure you threshold for your mechanism to see how much it actually needs. So we know that it's 0.16 meters. So how much, let's say we want our mechanism to trip whenever our block enters here. So we can see here that our block is about 0.06, 0.07 meters. So let's take a look at some of the configs here. So the configs we care about are under proximity params. So we have minimum signal strength. So that's the minimum signal strength for the signal to be valid. And we can actually take a look at that signal real quick. So if we look at signal strength here, we can see that our ambient signal strength is around 4,000. If we put the acrylic in front, we can actually see that our signal strength is roughly around the same. So it doesn't really change too much. You'll notice a more significant difference as you get closer. So as your mechanism's more closer, you actually see that our signal strength jump dramatically. So you can use this thresholding to kind of set a minimum bound for what you expect your mechanism to be at. Because if your signal strength is very low, I would expect your distance measurements to be very high, higher than what you would normally expect them to be. So you can use the signal strength measurement to kind of guard your distance measurements and know when you should really act upon them. So the other config I want to show is the threshold config. So the threshold config is the actual measurement before we start making the mechanism appear as detected. So before we get there and start making changes here, we know that our signal strength never really drops below like 3,500. So let's go ahead and bump that minimum signal strength up to 3,500. So 3,500. Our proximity threshold is, let's double check what that should be. So if we take a look at our distance, we want our threshold to trip at, what is this value? Around 0.6 meters. So let's go ahead and head back to that config. So we're gonna go ahead and tweak this threshold to 0.06 and apply that. And now we're not detected. Great. That's because there's nothing there. If I put the cube there, nothing detected, bring it closer, and now we're detected. Closer. And note that because of our proximity hysteresis, that's a big word there, you can actually see that there's a bit of wiggle room before we leave that detected state, and that's configurable through the hysteresis. So what is our proximity hysteresis? The proximity hysteresis is a value that when added to your threshold determines what you need, what the distance measurement should be to enter in a undetected state, and the proximity hysteresis when subtracted from your distance threshold is the value that you need to enter, that your distance measurement needs to be for it to enter a detected state. So for example, if our proximity threshold is 0.06 meters and to keep it simple, our proximity hysteresis is 0.01 meters, that means for the CANrange to enter into a detected state, it must see a distance of 0.05 meters. But for it to leave that undetected state, it needs to see a measured distance of 0.07 meters. And we're going to have a graphic shown on screen here that should help eliminate any ambiguity here. Generally though, 0.01 is kind of a nice sweet spot, but you should tune for your system. We have a couple of other configs here that are relevant. Looking at the time-of-flight params group, we have update frequency and update mode. So in the short-range user frequency and long-range user frequency, you can actually configure how fast the CANrange gets sensor updates. Generally, a good rule of thumb is that higher user frequencies are going to be more vulnerable to ambient lighting, but you get updates faster. A shorter or a smaller frequencies are going to result in more filtering, a little bit less noisy distance measurements, but at the cost of you get measurements a little bit slower. So you should profile to see, do you need 100 hertz, do you need 50 hertz? What is the minimum amount of time that you need to act upon a measurement? This combined with the distance and filtering configs allow you to have a lot of flexibility in using the CANrange reliably. The last config group I want to talk about is the FOV params. So that gives you field of view, center X, center Y, range X, range Y. And those are if you want to narrow or enlarge the beam that the CANrange sends out to determine distance. A shorter beam allows you to, let's say you have a really small hole that you want to shine the beam through. So you can actually tune that beam such that it shines through the hole if you want to minimize footprint. To help with tuning that process in the self-test, so if you capture a self-test of the CANrange, there is an FOV visualizer to see where the beam is going to be kind of offset from. The CANrange is an incredibly versatile sensor with a variety of applications, from localization to state management to limit switch tracking. We hope you choose CANrange for your next project. Make sure to visit ctr-electronics.com.